Another counting trick. I almost started with a picture of Sesame Street. We're going to do pigeons. We might as well have bird up here. What's a pigeon coop look like?
And that's with cage around it.
So I got a little nest, I got a cage around it. Okay. I want to think of sorting pigeons into their nests. Since pigeons were used as messengers, homing pigeons, they would return to their location of home from wherever they were. So if you raise them to be, hey, this is where you need to go back to, you can send messages back there whenever you want. So people would have large arrays of nests for their pigeons. So here's my question. What happens when you have more pigeons than nests? Consider objects as pigeons, containers, pigeonholes. You have more objects than you have places. What do you have to have? Now I'm going to put them all away. I'm going to put them all away. All the objects go into containers. But as you said, I'm going to have something left over, right? So what does that tell me about where I put that? One of the containers. That means at least one of the containers, at least one, must have more than one object. This originally had nothing to do with pigeons. The nickname of the pigeonhole principle came much later. This was coined by a gentleman by the name of Dirichlet. And he was talking about furniture. You have a whole bunch of clothes. You have a bureau, a dresser with drawers. If you've got 5 drawers and 6 shirts, what do you know is going to happen? At least one drawer will have at least 2 shirts in it. You could put the shirts away any way you want, right? You could put them all in one drawer. You could put one in each, and then there's 6 shirts got to go somewhere, right? But you're guaranteed to double up at least once. We've used this before. If I have a function, f from A to B, and I know the cardinality of A is strictly larger than the cardinality of B, what do I know about this function? At least one object in the range gets doubled up on. At the end of the semester, I'm going to post grades. How many grades are possible in this course? More than 5. But this course, like every course at Seton Hill, uses the pluses and minuses, right? So I'm sorry? There isn't an E in our grading system.
If you don't pass, or if you don't finish the.
That's an incomplete. You haven't earned a grade yet. That's not a grade, that's a hold. No, unfortunately, we don't. Which I think is wrong. But I didn't write the rules, I don't make this up. I got it in the course catalog, that's what it says. How many different options are there? There are 12 options here, right? How many students are in this class? More than 12. Guarantees me at least 2 of you get the same grade. Are you ready for the most absurd possible definition use of this? There are at least 2 people in the city of Pittsburgh that have the exact same number of hairs on their head. How can I possibly say that? That's a hell of a claim. Yeah, but I can actually go you one better. I don't even have to find people at all. I can say right now from here, this is going to be true. Liz, what?
The number of people in Pittsburgh exceeds the number of hairs that people have.
That would be a good question. How many hairs should a person have on their head? You have the internet. Look this up. How many hairs on a human head? Okay, 100,000. I'm going to give a margin of error. Let's say it's as much as 150,000, right? And if you bald, you have 0. So the numbers go from 0 to 150,000. How many people in the city of Pittsburgh? You have the internet.
$303,255 as of 2026.
Population of Pittsburgh, approximately 303,000. Number of hairs on a human head, 0 less than or equal to, and less than or equal to 150,000. 300,000 definitely bigger than 150,000. Line everybody up by how many hairs they have on their head. We're going to paint numbers from 0 to 150,000 on the ground. We're going to count people's heads and stand in place. I have to have at least 2 people standing the same number. Even if I don't find bald people. but I don't need to find them to know it has to be true. It also doesn't tell me which, right? It doesn't tell me what number has the matching people in it. It doesn't tell me which drawer. I don't know which grade two people are going to get. I can hope it's not an F. That's the idea here. I don't know which drawer is going to have two things in it, but at least one of them will. Questions?
That theorem, can you also say that if there's over double, that there's at least more than two in each section?
So let's up our numbers. Instead of just K plus 1, I'm going to make it N objects. So how many would be in my overflow container? All right, wait a minute. I have N objects. I've got K containers. Let me try and divide them as equally as possible to start with. So I'm going to take and divide N by K. But if that's not an equal number, I'll round it up by at least 1. So I'll use my ceiling function. In our case, 303,000 divided by 150,000 is 2 and change, right? It's 2 point something. So at least 3 people will have the same number of hairs on them.
Can there just be 2 twos? Like this person matches and this person matches over here, not 3?
There are 19 students in this class. There are only 3 rows of tables, right? 19 over 3. Say again?
19 over
19 over 3 is 6 and a remainder. At least one row has to have more than 6, which means it has to have at least 7. That happens to be this one. But if I spread you out as thin as possible, it would be 6, 6, 6, and then one other person. You have to go in one of these rows. The lowest possible number is N over K plus 1. It can't be 2 and 2, because I have 300,000 plus people. So I can lay out every category with 2 and still have 3,000 more people. Right? Numbers from 0 to 150,000. Every one of those gets 2. That's 300. That's 300,000 and 2. If they count at 0. But then I have 2,800 more people. Somebody's got to get a third person standing. It's got to be 3 in this case. More questions? So the pigeonhole principle in its simplest version tells me that if I have one more object than I have containers, I get something with 2. That's really K plus 1 over K is 1 with a remainder. You have to round it up. That's why this general version applies in more cases. There are 19 students in this class. How many of you were born in the same month? I have no idea what your birthdays are. None whatsoever. It could be that all 19 of you were born in the same month. I don't know that. But I know at least 2 people. Because 19 over 12 is 1 with a remainder. So I rounded up to 2. It may be 3, 4, 5, 6. I don't know. But it's got to be at least 2. Suppose that should actually be written right here. Should holds at least n over k objects rounded up. So if I ask you to pick cards from a standard deck, how many cards do you need to make sure you have 3 of the same suit? Why 18?
Because N would be 52.
Okay.
And then you need I should have divided by 4, not 3.
Please?
9,
Why 9?
there's 4 suits.
4 suits.
You want the 2 card be 8 plus 1 remaining.
I want number of cards I take sorted into 4 categories to be equal to 3. Which means I want n over 4 to be bigger than 2. And that means that n must be bigger than 8. We've got to start with at least 9 cards. You might get lucky and get 3 matching cards right off the bat. But if I deal them face down and I tell you, stop me when you are 100% sure that you have 3 cards that have a matching suit, then you have to wait until you get to card number 9. But there are 4 suits, right? What if I told you I wanted 3 hearts? You can't guarantee me 3 hearts will match. You only have 9 cards. The 3 matching cards might be clubs. The 3 matching cards might be diamonds. The 3 matching cards might be spades. I know that 3 of them match. I don't know which category they match in. That's him. But if I had 12 cards, it would be 3, 3, 3, 3, right? If I'm lucky. What's the worst possible thing that could happen in my first 12 cards? I don't get a single heart. They might all be spades, all be diamonds, all be clubs, right? Maybe I took this deck out and nobody shuffled it. And then the spades are on the top. I deal all 13 spades and I keep dealing. Again, what's the worst thing that could happen as I keep going?
All of the other suits before you didn't have a single heart.
Oh, crap. So how many cards go by before I get my 3 hearts?
I was gonna say 42.
39 cards go by. And those are all the clubs and all the diamonds and all the spades. And then my last 3 cards. So I need to approach this from 2 different sides. I need to think about, what could happen versus what's the worst that could happen. We did worst case analysis when we thought about algorithmic complexity, right? Remember our change-making algorithm. The worst possible thing that could happen is I only have 10 minutes. Oh crap, I'm gonna be here forever. Now, please note, I said you weren't allowed to stop me until you were 100% sure that you got the 3 hearts, right? If you're willing to take a risk here, we might be able to cut this number down. But that's going to require me to do a little more work beyond where we are today. So we're going to hold that thought until later in the semester. Questions? Exchanges and extensions, right? Phone number, area code, exchange, and extension. How many phone numbers per area code? I need to go back to what we did about the Telecommunications Act and remember what numbers are allowed where. What were our restrictions on any of these numbers? You wrote this down Friday. At least you should have, because I wrote it down Friday.
The first number cannot be a 0 or a 1.
Okay.
Second number, had to be a 0 or 1.
That
They
was
got rid of that.
that was in the old version. In the new version, it can be anything. As a matter of fact, that's the only number that had a restriction got rid of. So the only restriction that's still possible is right here. This number is not a 0 or a 1, and all of the rest of the numbers can be anything we want. How many options? Eight times 10 to the 6th. What's the population of the state of Pennsylvania? Internet is your friend. So if there are 13 million people in the state of Pennsylvania, how many area codes do we need in the state of Pennsylvania? Yet clearly that's not what's happening. So there's a disconnect between the number of people and the number of phone numbers, again, because of the way they sell and distribute phone numbers. Because we distribute phone numbers by exchange, we end up running out a lot quicker than we otherwise would. Even if there were 30 million people in this state, we'd still only need 4 area codes. We've got 10. Sure. So let's triple that number, right? So that's 39 million. 39 million. Every single human being in the state of Pennsylvania gets 3 phone numbers. How many area codes do we need for 39 million? 5. And there are 10. It's not that people have more than one phone, it's that phones are associated to locations. Phones are restricted to blocks of 10,000, so people buy the entire exchange at a time. They buy all 10,000 phone numbers rather than just the 3 they need. So we're not distributing them uniformly. Questions? The utility of the pigeonhole principle comes from the fact that I don't actually need to know which things match. I just need to know that they match. Here is a rather weird theorem. That's a really weird claim. If you looked at numbers between 1 and 100, and you pick 51 of them, you must have 2 numbers where 1 divides the other. I don't know which numbers you picked. If you write down a list of 51 numbers between 1 and 100, I guarantee there will be 2 numbers where 1 divides the other. And most of you are looking here, okay. I don't want you to believe me. Hell, I'll make it easy. Let's just do numbers from 1 to 10. I need you to write down 6 numbers. 6 numbers between 1 and 10. You cannot use the same number more than once. But if you use the same number more than once, you're done. Because then the same number divides itself. Use different numbers, 6 different numbers between 1 and 10. Roman, give me your 6 numbers.
4, 5, 2, 9.
Stop. 4, 2. 2 divides 4. I'm done.
Absolutely.
Yeah, you said 4, 5, 2, right?
5, 2, 9.
Oh, 5, 2, 7. 5, 2, 9, 7. Keep going. I need 2 more numbers. Aha! I don't care what number you pick. Give me a list of 6 numbers. Donna, do you have 6?
Yeah.
Give me 6.
1, 2, 3.
Stop. 1 and 2. 1 divides 2. If you try and wheel them out, you're going to run into trouble. But if you just randomly pick 6 numbers between 1 and 10, I guarantee you, one of them divides the other. $64,000 question. How do I know this? Where's the proof that this is always going to work? Maybe, Don, maybe I shouldn't pick 1. Ever. All right, I never pick 1. I'm still picking from 2 to 10. How do I know they have to divide? Every number between 1 and 2n is either even or odd. Yes? If it's even, it's got some power of 2 associated with it. 8. 8 is 2 to the third times 1. 12 is 2 squared times 3, right? So I can think of every number, even or odd, as some odd number times the power of 2. If my number's odd, then it's times 2 to the 0. If my number's even, I just keep factoring out all the 2's I can. So for I equals 1 to n plus 1, my selected number is 2 to the something times an odd number, a I. And I'm going to do that for all n plus 1 of my numbers, right? Now, qi is between 1 and 2n. Well, that means the same thing is true about ai. Yes? If this number is smaller than or equal to 2n, so is this one. Here's the sneaky part. How many possible values of ai are there? No. AI is the odd remainder after I divided out all the 2's, yes? How many odd numbers are there from 1 to 2n? How many odd numbers are there from 1 to 100? How many odd numbers are there from 1 to 10? Half of them, right? How many odd numbers from 1 to 100? How many odd numbers from 1 to 1,000? How many odd numbers from 1 to 2n?
2n divided by
2, which is just n. 2n divided by 2. It's less than or equal to 2n, but it's got to be odd. Wait a minute. My numbers q are the pigeons. The pigeonholes are the a values. How many numbers did I select? N plus 1. I have n plus 1 pigeons, and I have n pigeonholes. What does that mean? At least 2 of my numbers have the same value a. Now, I don't know which ones they are. I don't care which ones they are. I'm going to say, oh, I've got Q A. No, I've already used A. Q J, 2 to the K J A J, and Q L is 2 to the K L A L, but those are equal. So I'm going to take away the subscript from the A. QJ equals 2 to the KJA, and QL equals 2 to the KLA. How do I know which of those numbers divides the other one?
The bigger one's gonna be the smaller one times 2.
Well, times some power of 2, right?
Yeah.
So I just need to know which of those is bigger in terms of the power of 2. Without loss of generality, which one do you want to be bigger, J or L? Okay. Without loss of generality, assume Kj bigger than Kl. Then Qj is bigger than Ql. QL is 2 to the KL times A. Multiply that by 2 to the KJ minus KL. Some power of 2, right? When you multiply with the same base, what do you do to the powers? And when I add these two, what's going to happen to the KLs? QL divides into QJ. One number must divide the other every time without. Do I know which numbers do it? Nope. But it's whichever numbers are a power of 2 with the odd part common. So if I had 12 in there, that's 2 to the second times 3. If I have any other number that's divisible by 3, that's the one I'm going to use. $64,000 question. Who gives a... Seriously, why should I care? Let's start with brute force. Does anybody here not have an ATM card? Cash card? Right? You go to the bank and get money. Sorry. I go to the bank, I get money. How many numbers do I have to type in? That means there are only 10,000 pins possible. Period. That's not a very large number of potential passwords, is it? A brute force attack on an ATM machine works. I have a challenge for you all. Go watch Terminator 2. No, do not hit up the ATM machine. I am not black hatting this class. No. But if you go watch Terminator 2, Edward Furlong's character, the young John Connor, steals from ATMs exactly that way. He brute forces an ATM. I'd love to tell you this is a stupid idea. Every hashing algorithm generates a finite passcode set. Statistically, I need a much larger hash to safe my work, to protect my stuff. There's an entire branch of mathematics called Ramsey theory that deals with subsets of very large sets. And I mean gargantuan numbers. 2 to the 10 to the 113 is a small one. These numbers get ridiculously huge. Ramsey theory was used to do something called hypergraph theory. Advanced data science people, you'll see this eventually. Graph theory talks about objects and the relations between them. But if those relations are more than one-dimensional items, like I'm not just looking at who's got whose phone number, but I'm looking at who's got whose email address, who's got whose dorm address, et cetera, back and forth, more information, I can look at clustering in different ways. When I look at collections of sets like this, I look at things like power sets. And these sets get huge and unreasonably complicated. If I can prove things about the connections without explicitly calculating them all, I can rearrange my data to give me probabilistic. There's something happening here. Look at the way this data is related. Me, I don't do this stuff. Anybody engaged in cybersecurity is going to say, hey, where are the large IP address pings coming from? Where's the DNS server checking a lot? Who's generating network traffic of this type? From what ports? Useless garbage for me, but I'm not a CS person. I've rigged this example. This example is fairly small, but it's just about divisibility. If I look at a large data set, I can start asking, where are my commonalities? What's the minimum required set of commonalities I can end with in any pile of data? So I would love to tell you this is useless garbage and you're never going to see it. And I don't know why you would want to learn it, except for the fact that there are a ton of really good reasons for this. Wednesday, I'm going to look at a couple more pieces specific to how we count and arrange things. Because this was really about counting. At that point, I will have finished enough sections that I should have an exam. Normally, that would be 2 class periods after that day, right? So Wednesday, and then Friday, and then Monday, we'd have an exam the following Wednesday. There's just one problem. Easter. So, despite the fact that I'm going to do this on Wednesday, you don't get to turn that stuff into me until 4 class periods later, which puts our exam not after we get back, but the week after we get back. But it only covers through the material on Wednesday. So, I will see you all then. You have a wonderful rest of your day. If you came in late and still have stuff for me, come get my stuff for you.